May I request all the participants to mute their sounds and videos. We'll start the session within few minutes.
Good morning. I, Professor S.R. Bhargave, welcome you on behalf of Bharti Vidyapit, deemed to be University College of Engineering, Pune, on the fourth day, 1 week online faculty development program on research and engineering technology. Today's topic is sustainable approach to comfort. For this, we have Mr. Bhupinder Godara with us as a resource person. He is a mechanical engineer graduate from IIT Delhi. He did his MTech in thermal engineering from IIT Delhi. His interest in innovation and new cooling technology for sustainable environment began some 30 years back. With his final year BTech project to develop a prototype of low-cost food storage unit. His work experience is over 30 years, include working as a part of senior management in several companies of repute in the refrigeration and air conditioning industry. His like career Danfoss, ACME, Onida, and Ferrers Lloyd. During his product development work experience, he has led refrigeration and air conditioning product development from concept to market. Thousands of these products today serve customers of railway, telecom, and residential application with class-leading performance and energy efficiency. He has a wide international experience and has been a speaker at several international and national conferences for sustainable technology. He has published a research paper in Engineering Failure Analysis Journal based on a case study on his product design. Over a long span of his career, he has been connected to IIT Delhi for consultancy project and has been an external examiner for students' projects on several occasions. Most recently, in 2017, he independently taught third and fourth year BTech students of IIT Delhi a course on refrigeration and air conditioning product design. He is joined IIT Delhi as a professor of practice in mechanical engineering effective February 13, 2020. I welcome you, sir. Now I request Mr. Bhupinder Godara, sir, to please stand his presentation.
Okay, thank you for the introduction. It's a pleasure for me to be invited as a resource person on the faculty development program. I think in spite of constraints, the fact that we are seeing a commitment towards such program demonstrates that we are trying to translate every constraint into an opportunity. So my presentation today is around sustainable approach to comfort. If we look at a current scenario, we expect that by 2050, 70% of the world's estimated 10 billion inhabitants will be part of massive urban networks. So we today are at somewhere a little above 7 billion, and this rate of growth of population will lead to an additional, say, somewhere around 2.5 to 3 billion. So many inhabitants will be all wanting to migrate to and be in good quality environments, and that is why there will be a stress on energy consumption the way we know it today. So all of us have aspirations for an air-conditioned office, an air-conditioned car, an air-conditioned home, and all that is essentially an aspiration to stay comfortable in spite of whatever is the outside weather. Now, some of this needs to be calibrated, and it deserves to be re-looked at. Is it the most sustainable way of going forward to keep looking for technologies to satisfy all of these needs? For sure, any of us, if we walk into a comfortable environment, we feel good, we feel happier, and to that extent, this is a need. But the question is, how do we satisfy the need? Then increase in purchasing power and affordability of appliances. So if I look back when I started my first job in 1988, it was considered a luxury to have one air conditioner at home. And today it has come to a point where it's considered common in cities to have every room equipped with an air conditioner. So from something which is a luxury, which was to be enjoyed sometimes, where people were concerned about the cost of running it, today it is becoming a necessity. And that is because our habits have changed. And then also because there is affluence, because there is development, there is more purchasing power available. We see growth in industry, growth in jobs, and all that leads to a higher ability of young working executives to be able to spend on comfort and appliances. That leads to an increased demand for energy. Now here is an estimate to put some numbers in perspective. This is a published document where the Energy Information Administration International Energy Outlook has estimated. And if you look at this graph, the one on top in red color, it shows a significantly higher growth rate in Asia versus other countries that have been marked in other colors below. So most of the growth that is expected is going to happen out of Asia. And that makes us more responsible, being a part of Asia, and India being a very high growth, relative high growth country. And we are relatively low on the penetration of air conditioning. So penetration of air conditioning is a term that is commonly used in industry circles when we look at what percentage of the population has an air conditioner. So in 2006-07, this number used to be around 1.5%, and it's going now closer to 3%. And if you look at China, this number is well above 10%. So in India, if we just continue to let things be and let the growth happen as it is, we will see more than 3 times the air conditioner volumes that are there in the country today. Just a quick feedback. Am I audible? Is my speed okay? Some kind of a feedback I will appreciate, because we don't have the luxury of seeing each other. Are you able to follow me? Anyone in the audience?
Yes, sir.
Hello? So any feedback? You want me to be slow, fast, or everything is fine?
Yes, sir. You are audible, sir. Not a problem.
Okay, good. All right. Thank you. All right, then you can please switch off your mics, because I'm getting feedback now. All right, now let's look at this slide. We have something called the environment, which we are all used to. And in fact, in this challenging scenario with the corona, all of us have understood that when human activities slow down, the environment attempts to recuperate. It tends to come back to its natural state of balance. So there have been news reports where satellite pictures show that there were certain high temperature zones around parts of China that within 2 months became normal because of the controls that were imposed, because of lockdown, the scenarios which led to reduced or almost negligible human activity in places which were dominating, buzzing with activity, buzzing with vehicles, buzzing with use of energy. So the sustainability limit obviously was being exceeded, and there is always a risk that if we reach a certain point, then there may be no possibility of returning to where we are today. So there is a tremendous responsibility we have for future generations to keep our environment in a state of balance, so that the future generations, our children, grandchildren, and their children are able to enjoy life as we know it today. So sustainability limit is something like we consume oxygen and plants produce oxygen. So there is a state of balance. Now, if there is a healthy number of plants around and there are the right number of human beings, then there's a state of balance. However, if we cut down plants and if it is just human beings consuming oxygen, then the ability of the environment to replenish that gets constrained, sometimes choked, and sometimes it makes it reach unhealthy levels. So the question is, where do we go? Let's say air conditioning as we know it today, used for comfort, and if we were to not have any further innovations which are targeted towards sustainability, then we would reach a state where we would not be in a state of balance. So this is showing some kind of a scenario where the planet Earth, is seen, let's say 30 years from now, and it would have gone well above the sustainability limit. Now, sustainability by itself has a number of associated components. One way of quantifying it is what is the temperature rise of the Earth over the next 30 years. Another way to quantify it is global warming caused by refrigerants that are released into the environment. So refrigerants get into the environment because end of life, because they have leakages and several other factors. Then we have ozone. So ozone protects the Earth, and the ozone layer protects the Earth by blocking the harmful ultraviolet rays and solar radiation. So how does refrigerant impact the ozone layer? So we've seen that there is a chemical process because of the CFCs and the HCFCs, which leads to a release of a chlorine molecule, which leads to destruction of this ozone layer, and that leads to people getting exposed to harmful ultraviolet radiation. This was documented, led to an agreement, an international agreement to phase out HCFCs and CFCs. So R12, as you know, was a choice of refrigerants way back in the 80s and 90s, and now R12 is no more used in refrigerators across the world. And that is precisely because of understanding that there is a sustainability issue, there is a damage to the ozone layer, and there is an international agreement which leads to eliminating all those products which have this gas. So if we go without innovation, this is what happens. Now let's say, along with this, without innovation, the factors that are contributing are increase in population that we discussed in the previous slide, and higher energy use per person. As more and more people are buying appliances, the average energy use per person will go up. And this is across sectors. This energy use per person is not just air conditioning, it is even things like agriculture, things like transportation. In agriculture earlier, there was a lot of manual work that was being done. In fact, to the point that animals were used even for tilling. The moment we go to using tractors, using automated equipment for spraying pesticides and nutrients, the whole situation changes. So what happens now? if we use some technological innovation, and we're going to discuss some of it in the next few slides, together with that, if we have some regulatory legislation. So unchecked tendency is that we normally will not put in enough effort. And a good example is the California standards for refrigerators. So when I was doing my BTech project, I did a literature survey, and this is some time back, it was 87. So it turned out that in California in the 70s, there was no major innovation happening in the field of refrigeration. Refrigerators in particular. So refrigerators were made to cool faster and look good. And there were no other drivers for R&D people to improve the products. When California introduced a set of regulations, a lot of R&D effort, and R&D effort means budget, means people, understanding, product development, and finally products in the market. So it happened because of legislation. Legislation demanded that the refrigerator of a certain size may consume no more than X kilowatt hours per year. This innovation is not as simple as we say it. It requires industry alignment. It requires standards. It requires fairly transparent ways of rating the product, and then the conditions at which a product can no longer exist in the market has to be very, very specific. It cannot be that there is any element of doubt by which companies can get out of business without having been told in advance that, look, this is not something that's going to be allowed 2 years hence. So this combination of technology, innovation, responsible use of technology through regulatory legislation as well. And then what do? So we can change the scenario. So the future that would happen if we did nothing can be changed to a future which is significantly better. And that significantly better future would be a situation where we have something which is close to the sustainability limit. So the technology is affordable, and that's something very important. When we get to new technology, it cannot be that we make it so expensive that majority of the population cannot afford it. So we cannot stifle the aspirations for development. So therefore, affordable technology and sustainable technology, which keeps the overall disturbance to the environment within the limits of sustainability, within the limits of the environment recuperating itself. Now let's look at the relevance of air conditioning in our daily lives. We are already in summer, so no question of approaching. The moment we begin to think of summer, we begin to worry about the rising temperatures, the unbearable humidity, and millions of people all over the world will turn on air conditioning. In the year 2000, refrigeration and air conditioning was named among the 10 greatest mechanical engineering achievements of the 20th century. And this was according to a survey of American Society for Mechanical Engineers members. Refrigeration and air conditioning, as I mentioned earlier, has grown from a luxury to a necessity and contributes in many ways to an improved quality of life across the world. And when we look at refrigeration, it is the ability to transport frozen foods, to transport fruits and vegetables so that they're not perishing by the time they reach homes from remote areas, and also the ability of people to enjoy fruits and vegetables which are not available in their respective zones or countries. In the next few slides, we're going to look at some of the history of air conditioning, and in that history we will see some of the technologies which were very sustainable and simple, and that might also stimulate some thought as to what are the options today that we can build on and perhaps integrate some of what is still practical and relevant from the history. Now, the human need for experiencing chilled beverages and cool air. So chilled beverages means whether it is in India, it could be in the rural areas a glass of lassi, or it could be for someone in the urban environment a cold drink or some other beverage, and cool air. So even if we look at old times, there has always been an attempt to somehow keep the air temperature right and water cool, so that there is the joy of experience of having a chilled beverage or being in a comfortable place. Now, over the course of human history, technologies have been evolving and the level of sophistication has varied to address this cooling need of human beings in summers. Modern air conditioning units not only cool but also dehumidify, and they have the ability to heat in winters and humidify in winters, and then the necessity of ventilation is addressed through those units, and they also purify the air. So with the levels of particulate matter, high filter specifications are developed so that the inside environment is healthy and there is no risk to, for example, particles settling inside the lungs of human beings. And this is true for commercial systems, large systems where there are air handling units, and it is possible to design filters with relatively high pressure drop. And some of the simpler units like electrostatic precipitator concept translated into a domestic unit, or some forms of HEPA filters, there are attempts to integrate them into air purifiers at homes and all. And in some air conditioners, there is an improvement in technology, even in the residential segment, where we can see that features such as plasma air purification and some other things are marketed. And the whole objective there is to trap particulate matter while the air is being cooled or heated in case of winters. So now we go to the section on history of cooling. And here, let's look at some ancient cooling techniques. So hand fans are historically known to be used in China as early as 3,000 years back. In Egypt, paintings from about 2500 BC show slaves fanning jars of water to keep them cool. These vessels were porous enough to maintain wet surfaces to facilitate the evaporation process, and the evaporation process caused cooling. Herculaneum wall painting from about 70 AD depicts a leather water bottle used for cooling drinking water. So this picture on the right is from 70 AD. It's been preserved and found in Egypt, and shows, how long back, even in 70 AD, the need for having cold water was a dominant human need. Then, ladies of the court of Francis I sent to Portugal for earthen vessels, which would render the water cooler and more healthful. Then around 2nd century, inventor Ding Huan, he was a Chinese engineer in the Han Dynasty, invented what is likely the first rotary fan. It had 7 wheels that were 10 feet in diameter and was powered manually by slaves. Eventually, Chinese engineers would improve the design to start using flowing water to power it, and rotary fans thereafter saw use in other dynasties and going with prominence by driving it through streams. So the power source was replaced and they became more and more popular. Other parts of ancient India continue to be popular even today for drinking water. In fact, there are a set of people who would not like to have water from the refrigerator because in their minds it causes a cold because of the exceptionally low temperature, and they prefer the pitcher water, the earthen pot water, just because it doesn't go too low and it just satisfies the need, but sense that it is cool enough to be enjoyed at the same time, not too cold to lead to a cold or sore throat or things like that. So this technology continues to survive. It also then, I remember from my project, BTech project, where I was looking at a low-cost food storage unit, I surveyed available technologies, and I came across something which is referred to as Sheetak. In the word Sheetak, and it is essentially 2 earthen pots, one inside the other, and there is water in between these 2 pots. So most people who are familiar with this technology of pitchers, earthen pots, etc., would have seen this also, and it has a lid. So essentially, you keep the food in the inside vessel. The water is between the annular space that is created because the outer vessel and the inner vessel, and then you have a lid. So because of water evaporating through the outer clay vessel, or if I may use the word pitcher like surface, there is cooling produced, the water cools, and the inside contents also get chilled or get cooled. Also, the humidity is relatively high inside this pitcher. So if you're looking at fruits and vegetables, then vegetables, particularly the vegetables which have tendency to dry quickly, would stay fresher longer because you're addressing the need for high humidity as well as. Then there have been some ancient attempts to store ice or create ice. The Chinese are known to do that in about 1000 before Christ. 500 years later, the Egyptians and Indians also learned to leave earthenware pots out during cold nights to make ice. So on the right, if you see, there's a picture, and this is of Allahabad, and this is not too old. It is 1843. So in 1843, this is a scenario where on a cold winter night, earthen pots are placed outside, and they are placed outside on a bed of straw, so that there is the straw serves as insulation. And then there was also this whole understanding of what kind of straw will be best suited for making ice. And then there would be an expectation to identify the right level of wind and temperature at night to create the possibility of forming ice, and then that ice would be stored. So the combination that was used was night radiant cooling, and it would be possible on winter nights when the temperature was around 5 to 6 degrees centigrade at night. The shallow beds would be formed on earth with about a foot of straw insulation, and it supported shallow, so flat, low height earthen pots, and they were left open to the sky. It was possible to form 1.5 inches thick ice, and as I mentioned before, this picture is very illustrative. Other civilizations, as the Greeks, Romans and Hebrews, stored snow in pits and covered them with various insulating materials. In the 18th century, Europeans collected ice in the winter, salted it, wrapped it in flannel and stored it underground, where it was kept for months. Now I'm building all this so that we begin to appreciate how, when there was no technology like modern air conditioning, where we can run a compressor and create ice, people were making use of storing ice. So it was less, I would say, it was more environment friendly, or it was less demanding on the environment then. And while that may not be the most appropriate in its form as it was practiced then, it could stimulate as to how we can integrate, make use of it. So insulation, something we can build into as a concept. The difference of temperature between night and day is an opportunity which gives us room for making more sustainable air conditioning solutions. And evaporative cooling, on days when it is possible to have comfort just using evaporative cooling, can we integrate? Can we make an air conditioner which is smart, intelligent? It knows what to use when. So without compromising the need for comfort on humid days, can evaporative cooling become a source of augmented way of cooling without placing exorbitant energy demands on the grid? So then you can read the rest of the slide. When ice wasn't available or practical, people used cool cellars and placed goods underwater. So again, in Europe, there are examples where there would be a stream of cool water, and it would be used by some people for preserving milk by having a container dip into that stream. And then wooden boxes would be aligned with tin or zinc and insulated materials such as cork, sawdust or seaweed, and filled with snow or ice to keep it longer. Then here is another example. It's called yakchal. It's an ancient type of a refrigerator, and again it dates to 400 BC. It was made with special material, again, engineering of that time, clay, sand, egg whites, lime, goat hair, and ash. So all of this was a mixture that probably by experimental means was found to be the most insulating, as well as it could retain its shape. So while it was like a dome shape on top, underground there was storage space which was used to keep ice and sometimes even food. Then here I have a quote from N.A. Akbari. It was one of the gentlemen whose name I forget, but he kind of documented the process of cooling water in the times of Akbar. So saltpeter, which is a gunpowder, it also is used for creating a unique way of cooling water. So it's a saline earth, and they fill it in a perforated vessel, pour some water over it, collecting what drops through it, they boil it, clean it, and then let it crystallize. So this is the way of making saltpeter. It's coming from a certain form of saline earth. Then the formulation is written, so he's documented it very well. One seer, which is a little less than 1 liter or 1 kg of water, is put into a goblet of pewter or silver. So this is a vessel. The container is referred to as a pewter or silver, and then the vessel is closed, and 2.5 saves. So you can say 2.4 kg or so. Saltpeter is thrown into the vessel together with 5 kg of water. So seer is very close to, so you can say 5 liters of water. And in this mixture, the goblet is stirred around for a quarter hour. When the water in the goblet becomes cold, then it is taken out and used for serving the king, say maybe Akbar himself or his other members. So this is historical. So this is how saltpeter was used to create a one-time cooling effect, and the price is also given. 3/4 to 4 months per rupee. So for 1 rupee, you get 4 months would be 160 kg. This practice endured, and the example on the right shows a similar device from early 18th century in India. The flask, bulbous shaped to maximize the effect, would be spun quickly in the cooling water to enhance the chilling. And then this technology or this technique of using saltpeter did not reach Europe until the late Middle Ages. While there are references to some use of snow and ice to create deserts in Europe before the Renaissance, the use of saltpeter for cooling beverages doesn't appear in records until 16th century. Then there is another technology of using wet reeds. So one of the earliest known uses of comfort cooling comes from ancient Egypt in the form of evaporative. So wet cloth or reeds were hung in the windows and doorways anytime a breeze blew. So see how we are able to eliminate the need for even a fan. So the construction is such that it is high, where you have a possibility of wind coming from any side, and it gives an opportunity for these reeds to get to benefit from the flow of air and get evaporative cooling. So it would evaporate the water from the soaked reeds, and on top of the natural cooling effect due to evaporation, this allowed ancient Egyptians to benefit from the much needed moisture in addition to the respite from dry summer heat. Then in India, we are familiar with using khas in the conventional desert coolers, and before that it was a practice to use tatties or on windward doors and windows in summer. They were like screen doors covered with dry khaskhas grass, which was kept wet. So this dry khaskhas grass has another unique property, that is a very likable aroma. So you get a feeling of freshness and a certain perfume, natural perfume. And architecture also played a role in pre-modern temperature control. In traditional Middle Eastern construction, windows faced away from the sun and larger buildings featured wind towers designed to catch and circulate prevailing breezes inside the buildings. So see how when there are no fans, when there is no electricity, the way of constructing homes is sustainable in the sense that you're looking forward to how when there is wind, you will use the wind and use it for cooling the inside of the home. And this has been across civilizations, so not just Egypt or any other country, but across countries it was a common sense approach that if there is a flow of air, and we know that air movement leads to comfort, just try and figure out ways to build buildings in that manner. Now we look at modern air conditioning as to how we evolved from those non-power driven cooling methods to modern type of air conditioning where we make use of electrical power. So it was in 1914 that Willis Carrier achieved the first application of air conditioning in a residential Gates mansion in Minneapolis, Minnesota. It was a 7 feet high, 6 feet wide, and 20 feet long house. And the home, for various reasons, tragic reasons, that the person who owned it died at a young age. It never got used properly. But that is the first known case of air conditioning a residence. Then in 1931, Schultz and Sherman invent an individual room air conditioner which could sit on a window ledge. And that actually has been the design that has led to growth of residential air conditioners. So they became very popular and were initially limited to the wealthy because of the large price. And the systems costed $10,000 to $50,000 that time, which is equivalent to $120,000 to $600,000 today. If we look at the currency devaluation and everything. In 1950s, in a post-World War II economic boom, residential air conditioning becomes just another way to keep the. So more than 1 million units were sold in 1953 alone. So as the price came down, the volumes grew, and that's what, when technology becomes affordable, it is natural for more and more people to be able to use it, buy it, and then the impact on the environment consequently goes up. A little more on the history of air conditioning. So Alfred R. Wolf is known to have pioneered application of air conditioning in large building spaces. Steam engines were used to power 3 DC generators with. So this is an example of Carnegie Mellon Music Hall in New York, and this is an aqua ammonia absorption refrigeration plant which was chilling brine, and it was pumped to cooling demodifying coils of the trade floor air handling plants of New York Stock Exchange. Now this is a design that he made, operated successfully for 20 years. The purpose of getting him here is because very often he is not considered as a contributor to modern air conditioning. In reality, he built systems way before Carrier built systems, and they lasted for 20 years. Whereas the first Carrier built air conditioning system was taken off within a year and a half to 2 years of its installation. Then this is another air conditioning project that he handled, basically customers of Wolf, and then some other high-rise buildings, so St. Regis Hotel, Cornelius Vanderbilt 2 house in New York in 1892. So anything that was happening before 1902 was done by Alfred Wolf. Then it was on July 17, 1902, where Carrier, whose picture is there on the top right, he was tasked to solve a production problem at the Sackett and Willems printing and publishing company in Brooklyn, New York. So These were not the first time that he was handling some drawings. He had worked long enough for his employer, the Buffalo Forge Company, and since his graduation from Cornell University a year earlier, he was a modest but gifted engineer. And his projects before he handled the printing press production issue were a dry kiln and a coffee dryer. So this problem that the printing press was facing was very unique, and it required some means of removing moisture. So there was an offset printing process that was being used at the printing press, and whenever the humidity levels would go up, the paper would change dimensions, and ink would not get deposited at the exact same point. So if you look at layers of ink, they combine together to get two different colors. And if you've seen poor quality newspapers, you would see the blue color would be shifted from the red, creating a hazy image. So that was the specific problem that was assigned to Carrier when he was working with the Buffalo Forge Company. So he started, so like any engineer, he started to look at first what are the chemical means of removing moisture. So he looked at calcium chloride, and he found that calcium chloride does remove moisture, but it creates another problem. And that is salt spray droplets in air are added, and that wasn't suitable for the printing process. So then he experimented with steam coils to lower the temperature of air below its dew point. So instead of putting steam through the coils, he used chilled water through those heat exchangers. And this led to his final design that led to a coil to deliver 211 kilowatt of cooling, half of which was using cold lake airy water and half using mechanical refrigeration installed a year later. What Carrier managed to contribute uniquely was humidity control using dew point of air. So this was a breakthrough. Until this time, the relationship between dew point and humidity was not well understood, and there wasn't data about the properties of moist air at that time. So this is what appeared in one of the Ripley's Believe It or Not. It featured on the left hand side, you can see that while walking in a fog. So when he is walking in fog, he conceived how on a winter night where there is fog, he got an idea as to how he can remove moisture from air. So this was the unique thing that was contributed by the thought of removing moisture from air by cooling it. Some 80 million readers of Ripley's had their first glimpse of the father of modern air conditioning at that time. So the tagline is to dry air by producing artificial fog. The artificial fog was spraying chilled water into the air to take the air temperature below its dew point and therefore strip it of humidity. So again, the real contribution that Wallace Carrier made was publishing the first psychometric chart in the Buffalo Forge fan catalog. So he started experimenting. So Carrier's contribution was when there was no data, when there was no understanding about the relationship between moisture in air, he started to run experiments. He used water inside those heat exchangers, which were otherwise used for heating using steam. So he passed chilled water through them, and he began to create data. What happens when air is taken to a certain temperature? So when he had experimented with calcium chloride, he came to this understanding that absorbed moisture was exactly corresponding to the amount of latent heat that was released in the form of sensible heat. This observation led to a train of thought which eventually was to become important. The experiment disclosed the interaction of latent and sensible heat of water in air when its moisture content was altered without the addition or subtraction of external heat. So it also led to complementary experiments upon the process of evaporation of water into the air and finally into the development of principles upon which air conditioning was founded. The Sackett-Willems installation has been touted as the first scientifically designed air conditioning system, and in 1904, 2 years after after he first conceived the design, and 1 year after the installation, it revealed that relative humidity reduction was from 86% to 63%. And Carrier himself is later on quoted to have said that this design wasn't the final answer to humidity control. So it was actually a stepping stone to mastering technology, which finally led to being able to predict what is going to happen in a system that is cooled, where air is cooled using mechanical refrigeration. And essentially his true contribution was that he perfected dew point control and the development of psychometric chart. He continued to theorize an experiment which led him to develop dew point control as a means of accurately controlling humidity levels in air, and he got a patent for the apparatus that he developed. Now this is on the right, you see the rational psychometric formulae. So this was presented at the ASME annual meeting of 1911, and it brought science to what had earlier been the often hit or miss design of air conditioning systems. So in the process, he also became internationally famous, and the chart was updated and reprinted regularly, serving as an essential tool to generations of engineers. And even today, the psychometric chart that we use has been the evolved form of what Carrier had then created. So this is what he had presented in this 1911 the psychometric chart. You can see his handwritten notes on the vertical axis, but if you look at it broadly, it has all those parameters that are there today in the psychometric chart. So we have the saturation curve, as you can see. Let me use a highlighter. So here is the saturation curve, is exactly as we see it today, and then these are the constant relative humidity lines along this. On the vertical axis, we have grains of moisture, and of course there are certain other elements of the psychometric chart that, as we see it today, like the room sensible heat load line and all those opportunities are not there in this. But then this was a very good first start, and it was used by practicing engineers for designing of air conditioning equipment. Then here we have the apparatus for treating air for a textile plant. So the Chronicle Cotton Mills, North Carolina, and it was used for both fan heating as well as ventilating, and it was considered a central station. So it had the humidifying system. So it's the first unit that had a central station humidifying system. So this was a process application, a little different from comfort, and on the left is an elevation of the building along with the equipment room, and you can see the blower unit is here, which is taking air, and on the left, on the extreme right, is the equipment which is humidifying and heating. So in textile plants, control of humidity is very important for the yarn to be maintaining a certain property and not breaking too often. So because of this property of controlling humidity, textile plants began to adopt air conditioning systems. So textile industry was among the earliest and most enthusiastic adoptees of modern air conditioning. So New England Cotton, here they are working in a clean and efficient environment thanks to the air conditioning. Then this term air conditioning was coined by textile mill owner Stuart Kramer of North Carolina, And he used this term air conditioning for the first time in a patent he files to describe his technique for controlling the humidity and changing the air of textile factories. And it was in 1908 that G.B. Wilson becomes the first person to use the term in a textbook. And think of it today. It is so commonly used that we would rarely pause to think about how this came into being. Then centrifugal chillers. So when Carrier looked at dew point control and when the need began to expand, so more customers began to ask for air conditioning, there was a need to have a different compression technology. And centrifugal chillers came into being. So in 1922, Carrier unveiled the first centrifugal chiller, which opened the door to large-scale comfort air conditioning. This is a picture, not of the time that he built this machine, but later on he was chairman emeritus of the company that he founded, and he made a visit several years later to the first installation of chiller. And this is the picture of the chiller itself. Now, there were two breakthroughs that happened at that time. Ammonia, as we know, is toxic. It's very difficult. If there's a leak, you can't stand next to an ammonia system. I, in fact, happened to have the opportunity of working for a short while in a fertilizer plant where ammonia is extensively used, and it was quite a task to maintain processes which are leak-proof or which have no leaks at all the joints and flanges that invariably come in. So ammonia was at that time a nuisance, and it was replaced by a safer refrigerant, dichloroethylene. And then this power was switched. So instead of using a reciprocating compressor, it was a compressor that makes use of hydrodynamic pressure. And it reduced the size and allowed much larger spaces to be cooled. So it opened the door for large building air conditioning, like departmental stores, office buildings. And, so Carrier's installation of comfort air in the US House of Representatives in 1928 was a historic first in a decade of historic firsts. Then theater. So this is again a history by itself. Theaters in the US used to be shut in summers because it wasn't possible to keep them at comfortable enough temperatures. So when air conditioning solutions became available, there was an attempt to offer an air conditioned environment in these theaters and create an opportunity for business in the period these theaters would remain shut. So the Rivoli Theatre in New York found itself to be a heaven from the heat of summer. So think about a scenario where the climate is not friendly in some months of the year and people really have nowhere to go. And then a theatre announces that it is opening with air conditioning. So the advertising is around making people comfortable. So it would be a natural pull for people who have free time on summer afternoons, summer evenings to go there and not only enjoy the movie but also the comfortable environment. So it was an attraction point. It was a source of increased revenue and profit for the theatre owners. Then this is the building in California that was again cooled by using Carrier air conditioning. And then confectioners were among the first to adopt modern air conditioning because of the need to maintain humidity and temperature for manufacture of candy and sweets. So these are examples from historical applications to how in the mid-90s all of this was happening. Now let us look at some elements from theory perspective. So now let's look at a review of the first and second law of thermodynamics, and the whole objective is now to look at ideal systems and real systems. So we've seen some examples of historical systems, we'll see some examples of modern systems also. But first of all, a quick refresher on the first law is in any closed cycle, the net work done on the surroundings is equal to net heat gained from the surroundings. Very simple and straightforward. In the second law, what does it say is, in a closed cycle, a proportion of the heat has to be rejected for converting the remainder into work. Now that statement, if you want to quantify it, we come to the Carnot cycle. And the Carnot cycle is essentially an ideal cycle, ideal reversible cycle with heat gain and heat rejection at constant temperature and compression and expansion at constant entropy. So it is the cycle, closed cycle, that offers the highest theoretical efficiency of conversion of heat into work. And for cooling, what is important for us is the inverse Carnot cycle. And the inverse Carnot cycle coefficient of performance is the highest theoretical coefficient of performance for a refrigeration system. Now here is the Carnot cycle represented on a temperature entropy diagram. We can see A to B is the process of adding heat, B to C the process of creating work, C to D is rejecting heat to the sink, and then D to A will be the process of compression, isotropic compression. So this cycle, if it has no irreversibilities, offers the highest efficiency in a heat engine. Now, if you were to look at the inverse Carnot cycle, we will just change the direction of the arrows. So C to B would then become the compression process, and we would do work on the system. B to A would become the process of rejecting heat to the environment. A to D would be the expansion process, and D to C would be the process where we would remove heat from the area of interest, which could be the conditioned space or the refrigerated space. Now, a real system, because we would not like to have compression in the two-phase region. So this now we are moving from a temperature entropy diagram to a pressure enthalpy diagram. So this was temperature on the y-axis, entropy on the x-axis, and now we are switching to a pressure enthalpy diagram. So here we have pressure, we have enthalpy, and we have the saturation curve. All of the region inside this curve is a mixture of refrigerant and vapor. And there are lines on this chart which will tell us what is the quality of vapor, like what percentage of liquid and what percentage of vapor. Now, we would not want compression to happen in this region, because if we start ideally, so the first step is that to have the highest coefficient of performance for any refrigeration system, we would look at operating at constant temperature. And the two-phase region of a refrigerant allows us that opportunity, that unique opportunity, that when we are rejecting heat at the saturation pressure, the temperature is constant, and the quality of refrigerant changes from. So when it is absorbing heat, the quality would change from somewhere like 70% to 100% vapor. And if there was to be no pressure drop, then we would have the theoretical optimal cycle, which is the curve which is shown in black. So in this curve, we will take heat from the conditioned space on this line. So as we go from left to right, there is constant temperature, constant pressure, heat removal. Then we have isotropic compression, which is from this point to this point. Now, the real understanding we need is that we want compression to happen outside the two-phase region to avoid any damage and loss of lubricant if we were to be attempting compressing a two-phase mixture. So we do vapor compression, and that's why the name of this term, vapor compression cycle. So we need to cross the saturation curve In real systems, we're going to cross it, but in an ideal system, in an ideal theoretical cycle, we will stop here, we will do the compression, and then this is the inverse Rankine cycle. And then we have heat rejection to the atmosphere, to the ambient air, from this point until this point. So again, because we wanted constant pressure, constant temperature, so we will stop here, and from this point we will expand the refrigerant, again isotropically. In an ideal theoretical cycle, we will recover some work here. In a real cycle, we choose not to recover that work, and we use a simple device for isothalpic or adiabatic expansion. Also, in a real cycle, because we want to make sure there are no refrigerant droplet, that means there is no liquid refrigerant, we like to have a certain element of superheat. So the move from the saturation curve to the point where we stop over here is the superheat region, and then we will have compression. So the compression again in a real cycle will not be isoentropic because of friction, because of losses, pressure drops and all that. So it will be slightly tilted away from the isoentropic line. And then we will have a region where there is de-superheating, so the temperature drops from this point till we hit the saturation curve at constant pressure. And then as we go to the left, we have heat rejection at a constant temperature. So some part of this real cycle is closer to the theoretical optimal cycle. Then there is another point that we must keep in mind. We will always need a finite temperature difference between the environment to which we are rejecting heat and the temperature of the refrigerant. So that will build in some irreversibility in the system, and it will also cause a departure of the coefficient of performance from the optimal theoretical cycle to the real cycle. Same thing will happen here. To remove heat from the conditioned space, we need a temperature difference between the refrigerant and the temperature of the medium, air or water that is being used to condition the space where we want comfort. So these are the two parts which also bring in irreversibilities and have a penalty on the COP versus the theoretical optimal cycle. Now we go to the next slide, and this is a slide which gives some examples on where we are today and the opportunity that we have going forward. So if you look at air water heat pump using R290 as a refrigerant, and if we have a temperature of 2 and a water temperature of 35, so 35 is being used to keep the air warm. So we will have a COP of the inverse Carnot cycle, then we have a COP theoretical, which is of the ideal reverse or inverse Rankine cycle, and then there is a factor. So what is the theoretical COP efficiency that we can get? And then we have real systems, and then we have the real system. So here are the definitions. The coefficient of performance, Carnot, is the maximum possible COP for a reversible system with no losses. Theoretical is the maximum possible COP for a Rankine cycle. Rankine cycle is the vapor compression cycle. And remember, this is we are talking about inverse. So inverse Carnot cycle, inverse Rankine cycle, and then the efficiency coefficient of the Rankine divided by Carnot, and then the real system. So what are we trying to say here? Residential air conditioning using R410a. The ideal COP can be 36 and the theoretical can be 31.58, and real systems are where 3.5. Today we can see systems with 3.7 also, but there is a huge gap between the 3.7 and the 31, and this is opportunity for engineers. What are the newer technologies that we can deploy to get this number closer to the theoretical number? We will never get to 31.58 because we will always have some irreversibilities, but how closely can we approach this? This is too wide a gap, and this essentially is one of the key contributions I want to make, getting all of you understand this opportunity and how directionally we can put R&D effort, simulation effort, research effort to come much higher, and this will drive sustainability. So sustainability will be all about reducing the energy footprint, one part. Second part would be around making use of refrigerants that don't harm the environment. And then also there will be other elements. So in an earlier lecture, Professor Sanjeev Jain made a presentation around what impacts comfort. So there is, among many other things, it's also the psychological factor. How are we trained to feel comfortable? Some years back, maybe it was fine to be in an environment of 27 degrees or 29 degrees even in India, if there was sufficient air velocity. Then clothing, what kind of clothes are we wearing? When we get used to low temperatures, so say 22 to 24, our attire begins to change that way. We don't want to be feeling chilled, so we will wear a full sleeve shirt, we will wear maybe even thicker fabrics, and in some offices we would even come in a suit. Whereas if there was no air conditioning in summers, you would not think of a tie, you would not think of a suit. You would wear clothing which is breathable fabric, which tends to take advantage of the human perspiration. So those are other aspects of sustainability, but those aspects of sustainability together with the form of air conditioning design that we create. And here one of the important ways to evaluate any design is what is the gap of the real system. So these are systems that are being sold in the market. So the COP of a real system is an air conditioning product that you can buy in the market, or a chiller that is being installed on the rooftop of a hotel or a big industrial complex. And you can look at this number, 0.08, 0.88 to 0.08. So this chart, then again, we can look at cold room refrigeration. So again, the cold room refrigeration, what is it? What are the two temperatures? The temperature that we desire and the temperature to which we must reject heat. And we see 0.18 versus 0.87, 0.22 versus 0.70 for cold room freezer. So we can easily see a huge opportunity no matter which system we are looking at. So the message from this slide is that there is a potential that is not utilized. So there's plenty of room for improvement in air conditioning. So air conditioning as an industry has an opportunity because of this. This standalone can drive a lot of consultancy projects. It can drive a lot of engineering innovation. It can drive a lot of new product design. But then over and above this, for sustainability, we are looking at changing refrigerants. So we've undergone one full cycle of change of refrigerant because of ozone layer depletion. And for that reason, HCFCs are now being phased out. So you can see some volume of R22 refrigerators, but most of the market has moved to air conditioning market has moved to refrigerants which are not having any ozone depleting potential. So R410A, for example, has a zero ozone depleting potential. R32 has a zero ozone depleting potential. So both these refrigerants are being widely used in air conditioning products in the market today. However, for reasons of impact on global warming, so each of the refrigerants also has a global warming potential. And R410A has a global warming potential higher than the refrigerant that it replaces, R22. So there is going to be engineering development work because of the need to transition from high global warming refrigerants to low global warming refrigerants. Part of the switch from R410A to R32 has taken place because of this understanding that an R32 as a refrigerant will have a lower global warming potential than R410A. So three main drivers, of which one engineering effort for one has more or less got completed, which is phase out of ozone depleting substances in refrigeration air conditioning applications. But the move to low global warming potential refrigerants is there, and the move for higher energy efficiency products is there. So these two opportunities are still there for each of us to understand and contribute. And this is one of the core slides. This is one of the core opportunity drivers for sustainable systems. Now, let us develop on the understanding of these cycles and how they relate to real life performance. So the theoretical coefficient of performance is dependent on the refrigerant, because this curve more or less determines, what will be the difference in enthalpy from point 1 to point 2, which is the compression process, and how much of refrigeration effect will we get from the refrigerant. So if you look at the theoretical part, then always look at the black line. This is the inverse Rankine cycle. And the coefficient of performance, very simply, all of you must be familiar with it already. It's the heat rejected divided by the isotropic compression work, which is the equation here. Now, in a real system, what are the other things that we need to be aware of? In addition to this work, we will also have some fan power. So we're going to run a fan on the indoor side, perhaps on the outdoor side, perhaps. Except for a refrigerator where there is natural convection on the outside, air conditioning systems will have a fan both for the indoor and the outdoor air movement. Then we will have some controls which will consume some parasitic power, and we would also have the temperatures in lower from the ideal cycle to the real cycle, so that we create an affordable system. So the size of the heat exchanger will depend on the delta T, the temperature difference between the medium being cooled and the refrigerant temperature. So this you can see over here, the difference between the red and the black. And again, here to reject heat to the environment, again we need to take it to a temperature higher. So in the condenser, the refrigerant temperature has to be higher than the temperature to which we want to reject heat, whether it is a water-cooled condenser or an air-cooled condenser. So these factors, then the compressor will never have isoentropic compression. So there will be an isoentropic efficiency. How close is it to the isoentropic compression process? This is because of the lubrication needs. This is because of pressure drops in the valves and some of the heat addition that is happening in the compression process because of the pistons rubbing against the cylinder walls. And then also life of the unit. So as units are used, dust accumulates. So accumulated dust on either side in an air-to-air system. So if you're using a air-cooled evaporator, air-cooled condenser, direct expansion evaporator, then air is coming in contact with the heat exchanger directly. So this leads to some build-up of dust. Or if the filter is not cleaned, then there will be a pressure drop that will increase, the airflow will come down. So we will depart from the design condition to a relatively inefficient point of operation. So these are the four parameters. When we say heat exchangers are too small and injection is not optimized, in a heat exchanger we need to divide the refrigerant over several circuits. And those circuits need to be such that in every circuit the heat added is almost the same, so that refrigerant leaving every circuit is at a state which is similar. So we have a superheat that is close to each other. Now this is never possible to achieve practically an exact value of superheat because of the nature of distribution of air and practical systems. But the closer we have circuit by circuit superheat analysis, the more efficient a system will be. So when we are designing systems, we need to take care of this first part. Compressors we've discussed. Then this part we will discuss in the subsequent slides. The system not able to compensate for varying load conditions. It's essentially an air conditioner. If you buy a 1.5 ton air conditioner for your bedroom, you cannot be sure that the load is going to be 1.5 ton all the time. There will be days when it will be less, and there could be a few days when it might exceed for a few hours. So when we are looking at optimizing systems, we will look at optimizing each and every component. So when we look at something which was the dotted line representing the technology without innovation, and we have the black cycle represented in black representing the theoretical optimal cycle, when we were looking at numbers, we are actually trying to drive this whole technology process from the dotted red line to the gray line. So somewhere between these two, we can reach a point which will be a solution which has a lower energy footprint, and to that extent it will be more sustainable. So one is we improve the circuiting, we reduce the temperature difference in the evaporator, and that would be one way of getting this line shift from here to here. Then we can look for compression technology, which is more closely resembling the isoentropic process. So if the compressor was redesigned with an eye on efficiency, we could look at better lubricants, we could look at closer tolerances, we could look at material wear characteristics which are different, and we could look at valves which are having a lower pressure drop. We could even look at compression technology which changes. So instead of using a reciprocating compressor, can we use a straw compressor? Is a rotary compressor better than the reciprocating compressor? Those are the situations that will come to mind when we are looking at compression technology. And in case of large systems, do we go to a screw compressor or do we go to a centrifugal compressor? Again, an opportunity for moving closer to the theoretical optimal side. What do we do on the condenser? Same, what we said here applies to the condenser. Here again, we need to do circuiting. We need to divide the refrigerant into different paths such that the heat rejected is similar, and here instead of targeting comparable superheat at the outlet, we look at targeting comparable subcooling. And then this process requires better control in terms of regulating the refrigerant flow in response to the changing scenario as here. But right now, if you're looking at steady state condition, we would size the expansion device such that it is closely matching the pressure drop that is required here. Then we have looked at this from a refrigeration perspective, but a compressor will also require a motor, an electrical motor that will be driving this compressor. So for smaller systems, it is common to use hermetically sealed systems. So the residential products that we buy today would have a hermetically sealed compressor, which means the motor is enclosed in a way that there is no shaft seal requirement. So the electrical motor is enclosed fully in a shell where the compression process is taking place, and we also make use of refrigerant to cool the motor. Depending on the type of technology that we are using. So if we use a reciprocating compressor or a scroll compressor, then we will have refrigerant come in from the evaporator and it will pass over the motor before it goes in for compression. So that has two major impacts. One is that the compressor motor gets cooled. The second is if there are any fine droplets in the refrigerant, they will all evaporate because the compressor heat, and then we can be sure that the compression process will have no liquid particles in it. So these are the important parameters as far as this particular slide is concerned. So the chart I'm using here is an R134a chart, and that is just for illustration purposes. This entire set of comments that I have shared with you will apply for any refrigerant that you use. If we were to use a rotary compressor, then what happens is that the heat rejection of the motor happens in the discharge gas. So then we will have some change in this part of the cycle. So the compressor motor would have rejected some additional heat in this point. So this point would move towards the right from the ideal theoretical cycle. It would move towards the right because of the heat addition. Whereas in a scroll or a reciprocating compressor, the heat addition to cool the motor is happening right here. So this would be a little more severe penalty on the coefficient of performance, but it is always accepted because of the reliability impact that it has. So there will always be trade-offs in any rail system. What is important? So we want a system which can last more than 10 years. So we want the compressor life to be in excess of 10 years. So for that, we will have to look at technologies that will ensure that anything that can mechanically damage the compressor should be avoided. And one of them is liquid refrigerant. So therefore, it is accepted to have this in the straw and in the reciprocating compressors. In case of rotary compressors, the design is a little different, and it is also one of the reasons why, if you look at catalog performances, rotaries are able to do better because of this difference in the way heat is rejected to the environment, to the refrigerant. Okay, give me a minute, please. Okay, I'm back. Sorry for the brief pause. I just wanted to take a bit of water. So now, having looked at this situation, which is optimizing for a steady state condition, now we will look at a real life scenario. So in a real life scenario, we will have variations in operating conditions. We know there is a variation of temperature in summer and in winter. We also know there's a temperature variation during the day, mornings to afternoons, late afternoons and night. And we have variations in the inside conditions. So we would like to have a slightly lower temperature during the day. We would prefer a slightly higher temperature for cooling at night, so that we are not disturbed. We are not looking for quilts and furs, but we have an undisturbed sleep. So the real life scenario is far from a steady state condition. So it's simple. You know, when you define a condition that we want to maintain 2719, the standard test conditions for an air conditioner when they are tested in a balance ambient calorimeter or a psychometric calorimeter. So it's common to have defined conditions, and then in my own experience, it was very clear. We would target a certain performance under those conditions. So if we had a number, like we want to have an energy efficiency ratio of, let's say 3.3 for a high efficiency unit, then once we test it and get the 3.3 number, we consider the project close to completion. So we just need to make the specifications and ensure there is repeatability, and then that product is ready to go to market. However, when we look at the impact on the environment, then that number, if we hit 3.3 and if it is being sent to market with 3.3, is not truly representative of what this product is going to consume, the amount of energy that it is going to consume. So well-optimized system at 35 degrees outdoor air temperature, 2719 indoor air condition temperature will not behave the same at 45 degrees outdoor air temperature. And now, what is the percentage derating? What happens when the temperature goes up? That's a factor, that's an influence of design. How robust is the design? How well have we factored airflow in the condenser? And how does it change? So do we have any technology which can sense that the outdoor temperature is going up and therefore the airflow must be increased? Are we having any technology by which we can monitor the performance of the unit when it is operating in a real life scenario with varying conditions? So let's look at ways to analyze that now. This is called the condition of shifting loads. Now shifting loads, let's for a moment assume that the evaporator side is constant. So we are happy with 25 degrees and we want to maintain it at 25 degrees centigrade all the time. Now if the compressor has a constant capacity, it will not be in a position to follow the best available technology cycle. So this from the previous slide, the gray color representation is of the best available technology. So if we put in all the components and they're optimized and we get them to their ideal or rather the optimum performance state, then that is what the gray lines represent. When the compressor is not varying in capacity, then it will have different conditions and different ways to meet different conditions. So here is the case, the temperature will go up because of the ambient temperature going up, and it will come down when the ambient temperature comes down. They are able to adapt to load and then allow the heat exchangers to have lower temperature difference. If we had, let's say, 50% of the capacity required at night for a residential air conditioner, it would be possible to make use of a lower temperature difference and get a higher efficiency because of a lower refrigerant flow rate. So the heat exchanger surface area continues to be available to us, but the cooling load has reduced, so we can reduce the refrigerant flow rate and we can benefit from a shift in load and reduce delta T on the evaporator side. Same thing at night, the temperature has gone down, so we can also bring this closer to the ideal inverse Rankine cycle. So these opportunities show up because if we move to a technology which is not a fixed on-off type of compressor, but a variable speed compressor. Now, when we are adjusting the compressor speed, we also need to match the pressure drop on the other side, and for that reason, we must have some means of an continuously adapting expansion device. So, if we were to use a low-cost capillary, then a low-cost capillary would have a fixed pressure drop for a certain refrigerant flow rate, and we could look at the curves and the performance of the capillary at varying conditions, and we could look at some means of optimizing that low-cost design also. But if we had an active element and we know that the compressor has come down to, let's say, 70% of its capacity, and then this expansion device also knows that now it needs to only allow 70% of the capacity, then that is possible through electronic expansion valves. So here we are talking about now technology which is continuously adapting to changes in the environment and load. So we have the ability to change in response to reduction in load or increase in load, and we have the opportunity to change the condensing temperature also in response to change in ambient. Now we need to look at a new paradigm for sustainable air conditioning products. And what would be some parameter that we could use for sustainable air conditioning? So one of the thing is the lowest life cycle cost, LLCC. L for the first L is for lowest, then L is for life cycle cost. So LLCC. Sorry, did someone say something? I couldn't hear you. Hello. Was there a question? Hello. Hello. I could hear someone speak. So is there a question or is this just some inadvertent noise? Okay, I'm assuming it's inadvertent noise. We'll go ahead. So now, what is the new design approach, or do we need a new design approach? Now on that I'm clear that we need a new design approach, because as we saw, if we don't make changes to our approach, then we will cross the sustainability limit. So we need to look at a new design approach, and then what are the elements that will be forming a part of the new design approach. So we have discussed systems. We'll need to look at standards. So once we make new designs available, there's a new approach to looking at sustainable design. We need to be able to measure the impact, whether it is part load efficiency, varying load condition, and low ambient condition performances. There will have to be some standards and then test methods to ensure compliance to those standards, and then there will have to be a backbone of a component industry. So if you want to have compressors that can change in capacity from 100% to 30%, then we need to say what is the efficiency that we are expecting at 30%. How will that lower efficiency work together with the larger surface area of condenser and larger surface area in the evaporator at part load conditions? So some means of simulation. So we need to have tools to simulate these conditions. and we need to have electronics that will communicate conditions from one part of the system to another part of the system. So this paradigm shift is what is needed for us to start looking at variable speed systems which are continuously adapting. The conventional design approach is what? The product is designed for standard indoor and outdoor conditions. As I said, when I'm designing in the conventional way, I have a number to hit. If I want to hit 3.3 EER at design conditions, once I've hit that number, my job is done. And the product then goes to the next phase. Release to production, then production looks at everything, and then it is going to market. And in market, it is going to be audited. If there is an energy labeling standard, for example, that energy labeling standard that we have in India, and just to divert the discussion a little bit differently, when I started working for Carrier in 2001, we had an opportunity to benchmark different products sold in the market. And since the 1.5 ton was the largest selling air conditioning product, so we picked up units from the market and we tested them for performance. And what we find is that every manufacturer had a deviation from rated capacity. And the deviation was in most cases in excess of 10%. There were manufacturers who had designed their product 1.5 ton minus 10% was their design condition. And they were expecting to benefit from the lower cost, which would lead to a lower price and therefore high volume. And there was no standard. There was no challenge testing regime. So it could be that if you were buying an air conditioner in the period 1999 to 2006, you would have bought a product which you thought was 1.5 ton cooling capacity, but it was giving you maybe 1.3 tons. Now, to look at one company having an ethical way of monitoring performance and the rest of the players not having a very ethical approach to performance leads to an imbalance where the customer doesn't know what is happening. So customers would simply go and buy a 1.5 ton product, brand A, brand B, brand C. And no visibility on the performance. So the Bureau of Energy Efficiency formed a team and they invited manufacturers to participate in the technology development of test standards. So I had the opportunity to be a part of the team and I had a fairly important role in terms of getting different R&D representatives from companies come together, understand on and agree on a transparent approach, which was not favoring any manufacturer, but which was performance oriented. So while the market that time was on 1.5 ton or 18,000 BTU per hour and energy efficiency expressed as BTU per hour per watt, we agreed on a dimensionless number as per the international standard. We looked at a dimensionless number and we defined bands of EER that would be put on the product. And we also had to define the test method. So what test method would be used so that there is no element of doubt. Manufacturer tests at his labs and then it goes to another lab and there's a difference and all that. And there could be a lot of controversy around numbers. So we had to agree on a test method, and a balanced ambient calorimeter test method was then agreed as the method of testing. So this whole development was happening in 2005 and there was no balanced ambient calorimeter lab in the country. So then there had to be a balanced ambient calorimeter lab set up, and one of the companies set it up just for purposes of supporting the need for testing air conditioners. So that lab was set up and it is not very far from our institute. And subsequent to that, many other companies also put up test labs, balanced ambient calorimeter test labs. And then we had to look at revising the Indian standard. The Indian standard at that time had not been revised to make it consistent with these new requirements. There were certain changes required in different clauses. So fairly good standard, but it was in need of revision. So we went to Bureau of Indian Standards. We were part of the technical committee there. And I'm sharing all this for you to know that when technology changes, when technology evolves, when the market expectations are changing, and when we want to drive sustainability, then all these elements, sometimes they are very time consuming, like taking 2 years to set up a lab that can give accurate data. But finally, things moved. And there was a voluntary phase in 2007 when manufacturers started labeling their products voluntarily. And 2 to 3 years later, it was made mandatory. And then the regulatory approach came in, which we're going to discuss towards the end of this lecture. The point here is that evolving situations and focus on sustainability requires managing technology, standards, and labeling programs together. So when we look at a product designed for standard conditions, we take it to a balanced ambient calorimeter, we verify the number, and then we are done with it. However, when we have something which is not at one condition but at varying conditions, then we need to have a different standard. And that standard was created and evolved later. So that becomes a tool to show the advantage of a variable speed system versus a fixed speed system. Now, important thing is that when you look at a variable speed system, then we can't look at fixed point performance. Then we need to make assumptions on what percentage of the time during its life an air conditioner will work at part load conditions. So what weight do we assign to the energy efficiency ratio at part load, and what weight do we assign to the energy efficiency ratio at full load? And one of the handy things, one of the handy analysis that comes in useful in making that decision is what percentage of the time in a year is the temperature in different bands. So we can make a temperature bin, like temperature from, for Delhi for example, let's say temperature above 30 for how many days, how many hours in a year. And then that we can again subdivide into 35 to 37, 38 to 39, and so on. And then looking at the number of hours in a year, looking at some 10-year data, historic data of temperature, and making some assumptions on what is the urban heat factor, which means when air conditioners are put together in a cluster, what impact that can have. So all that can be integrated into an analysis, and we reach a point that yes, this is what we can see that is a reasonable number looking at temperature variations and conditions of part load because of the customer's load being lower than what the unit is designed for. And the load also is a function of outside temperature, because when the outside temperature is less, the heat gain through the walls, the heat gain through the roof, the heat gain through infiltration, all of that also reduces. So here is a little more formal description. The product in a conventional design is meant for a standard indoor and outdoor condition. So for example, if you look at the ISO 5151, the outdoor ambient temperature is 35 degrees centigrade dry bulb temperature and 24 degrees centigrade wet bulb temperature. And the indoor conditions are 27 degrees centigrade dry bulb and 19 degrees centigrade wet bulb temperature. So this is the condition, and if some of you are not familiar with these conditions, you might think 27 is too high. Essentially, it's a return air temperature. So if we are sitting in a room which is at 25, there will be a temperature rise between the temperature we are experiencing and the temperature that goes to the heat exchanger. So some part of it is that, and some part of it is more, standardization with other standards internationally. So it is a number that is matching with the standards used in Europe, US, and Australia. So to that extent, there is harmonization of the standard also. Now this test requires cooling capacity and power consumption to be measured when steady state conditions are achieved. So we need to run the air conditioner such that for a period of 1 hour, for readings taken at intervals of 10 minutes, the change in these conditions does not exceed a certain number that is defined in the standard. I think it's either 0.2 or so. So once we get that level of stability, then we calculate the cooling capacity of the unit, and that becomes our indicator of rating the unit. We measure cooling capacity, we measure power consumption, and then it's not just sufficient to have a measure of this fixed speed, fixed rating point capacity. We also need to be sure that this unit will work satisfactorily when the temperatures are high. And for that, there is a max operating condition test. So for the max operating condition test, we raise the outside temperature. So in the Indian standard, we would see that the outside temperature needs to be increased to 46. the inside temperature needs to be increased to 35. So we take a scenario commonly in a home. You walk into a room on a summer day, afternoon time. Outside temperature could be in the region of 46, and the inside temperature could be high because there was no air conditioning before you entered. So when you switch on the AC, it should be able to operate without tripping. So a test is performed where this unit is run under those conditions for 2 hours. And having run it for 2 hours, then the unit is switched off. It's kept off for 3 minutes. That is to give the compressor requisite time to have pressure equalization, and switched on. So it needs to get switched on, and it should not trip. So that becomes a reliability test. So that when this product is being used by customers, they will, while they get the desired performance in terms of cooling number and they get the desired energy efficiency ratio, they also have no reliability issues. And if we enforce this test across manufacturers, then there is no problem. Everyone is having to meet the same performance and reliability expectation. So now imagine the impact this had. So once this whole thing for conventional fixed speed systems came into operation, the air conditioning industry had to put in R&D investments to get this number right. Now the limitations of the method that we've just talked about are that it's no guarantee of what will happen in the real operating conditions. And only for a small period of the entire operating life of the AC will we see these test conditions matching the actual conditions. So then we look at varying ambient and load conditions, which make this complex, as we had discussed in the previous slides on the pressure and enthalpy diagram. However, variable speed air conditioning offers us these opportunities. So it's an opportunity for closely following the best available technology cycle in changing load scenarios and changing ambient conditions. And also it helps us move towards a life cycle cost analysis on annual energy cost basis. So even if we look at it, if we put aside the sustainability advantage and just look at energy costs, a variable system would promise a lower overall energy cost versus a fixed speed system because of the opportunity at part load conditions. Same heat exchanger, same compressor, but with technology to vary the speed, will allow the heat exchangers to be better utilized. There will be no off cycle. There will only be part load and full load. And the part load will far exceed maybe something like 70% of the time, or even, well, actually, if we do the right design calculations for sizing the unit, then 98% of the time the unit will operate at part load. And then what part load will vary. So 95% how much, and 50% how much, and 10% how much is going to be a separate discussion based on the weather and the load conditions. But it is for sure going to lead to this opportunity to save energy costs. Now, while we are saving energy costs, because we are reducing the electricity consumption, therefore less coal will be burned to generate power, or less any other fuel that we use. So to that extent, and even if it is nuclear, we need to use less energy, so more people can be satisfied with the same energy availability. So whichever way you look at it, any technology which offers reduction of annual energy is going to be good towards the welfare of the environment and for the welfare of the population, the citizens. Now, these are some slides just to give you a glimpse of what is there inside a compressor. So most of the manufacturers today want to use a permanent magnet DC brushless motor with in-slot winding, and then there is a positive displacement oil pump. So see, the challenges that come in when you look at changing the speed of the compressor to regulate capacity is that when the speed of the compressor goes down, the oil will not be sufficient during low speeds to ensure that there is proper lubrication. So for that reason, there needs to be a different technology. So maybe a pump is needed. So that is integrated. Then you have a compressor motor protection, so that if for any scenario where the motor experiences overload, it can be protected and there is no burnout. So these things happen because of varying loads leading to high discharge gas temperatures, particularly in scroll compressors, and that can happen because of short durations of high superheat being encountered when the load changes from part load to full load, and there is a delay in the refrigerant being available to the coil. So this is so oil management inside the compressor becomes a big technological challenge we need to be aware of, and then we innovate. So we create solutions to that. So now when we look at variable speed compressor technology, we need to look at motor design for high part load efficiency. If we use a standard squirrel cage motor, its part load efficiency is very poor. So we need to have a motor which is designed for a higher efficiency across the range of operation. At inverters and then some controllers and sensors and a matching of all these components. So a lot of intelligence needs to be built in. What happens when the load goes low, the compressor speed goes low, the expansion valve needs to change. It needs to allow for less refrigerant to be flowing for the same pressure drop or for a reduced pressure drop. At the same time, we want to be sure that the compressor operating envelope, which means the combination of pressures and temperatures on the suction and the discharge, they are not exceeded. The current that is being drawn by the motor is not going above what it is rated for. So all of this knowledge has to be built in and put into a software algorithm so that we ensure reliable operation throughout the life of this product. This slide has more detail than necessary for the purposes of this discussion. I would say it simply is elaborating on the communication needs. We must always be aware that any electronics will be exposed to high temperatures in a country like India. If the temperature is 45, you might see 52 or more inside a closed cabinet, and you need a closed cabinet because of reasons of protection from dust and moisture. And then we need to think of what communication protocol will we use when we are communicating from the user interface where we are defining the temperature to what controls the compressor to what controls the expansion valve, and then how do we protect the inverter itself, which is going to be driving the variable speed motor. What happens in coastal regions where there could be some element of salt and that could be corrosive. And then there is an impact always on the power factor because of all this inverter technology being used to drive variable speed motors. This is an electronic expansion valve controller. So you can see there is a stepper motor valve, which is, let me bring the pointer here. So this is the stepper motor valve. As the refrigerant is controlled by defining the duration of opening and closing of the solenoid valve, and that is being communicated and controlled from here. Then there is a need to get to know what is the superheat. An expansion valve is expected to maintain a constant superheat at compressor inlet. So we need to have temperature sensing, pressure sensing, and then some other functions like indirect loss of charge detection, which is if refrigerant leaks, can we find that out? And then can we define what maximum pressure we are going to allow for this unit to operate? Because the evaporator is at part load, the pressures can go high. So we need to have that built in. We need to comply to standards, we need to comply to EMC requirements, and we need to have a good communication, and then we also need to be able to fit this in a particular size. So all of this is important. Now here this diagram shows us some of the interconnections and interrelationships. So the expansion valve, the controller is right here. Then this is going to take some feedback from here as well. And the evaporator coil is fed from the expansion valve. So refrigerant comes in here. And then from here it goes to the suction of the compressor. We need to sense the temperature and pressure at the outlet of the evaporator and before the refrigerant goes to the compressor. So we need to have a pressure sensor and a temperature sensor. And then all of these are, as I mentioned before, need to be integrated. So we need to have a discharge pressure sensor. We need to have a surface temperature for the discharge gas. Then do we need to run the condenser fan at its full speed all the time, or do we need to vary the speed? What is the ambient air temperature? So the ambient air temperature can help us determine we need to run it at full speed, part of the speed. And the pressure that we get from the condenser tells us also how well we are doing on the airflow characteristics. Because we need to maintain a certain pressure for heat rejection. We need to maintain a certain pressure drop across the expansion valve for refrigerant flow to happen. And all that is a lot of work for engineers to look at all these varying conditions, then test the product. So not just do the simulation part of it or the design part of it, but also then devise the test method so that we can be sure that if we got down to a certain percentage, let's say we design it for 30% part load, then at 30% we should be able to run the unit. Not that most of the time we are finding it overloaded because the suction pressure has gone up. And that would be defeating the purpose of design. So if it is designed 30%, it should operate reliably. For field conditions leading to some choking of the evaporator coil or anything else, we would have the safeties and the ability to switch off the unit. Then what else do we have from here to here? We could have, this is another example of a A-shaped coil, and that is used in the evaporator. And this is another way of applying it. Now, line branching becomes another important part of multi-indoor systems, VRF systems, variable refrigerant flow. VRF stands for variable refrigerant flow systems. So we have, typically in a commercial application, so in an office you have several of these are cassette units with a corded remote. So all of these are evaporators where we are taking heat from the occupied space, and then the refrigerant is being merged. As you can see, there's a particular type of a connector here, then another connector here, and all of this goes into the condensing unit. So all the refrigerant is going there. So there has to be a way to estimate the pressure drops and ensure that flow occurs through all of these branches in the desired fashion. And mind you, there will always be, you will be feeding as well as taking refrigerant back. Now, what are the expectations we can have from a variable speed system? The first thing is that it is going to lead to a more precise temperature control. So if we sit in front of a normal window or a split air conditioner where the compressor goes on and off, particularly on humid days, we can feel sense the air quality. It is changing. When the compressor goes off, we can feel that there's a bit of humidity and the smell is not fresh anymore. Whereas when it is running, at that time we tend to like the odor and the overall sense of freshness in the air. That is because there is a dehumidification part that is happening all the time. And in the off cycle, what happens is that the air picks back the moisture that was condensing, because there were drops of water on the coil, and then we switch off the compressor because we met the room temperature, the dry bulb temperature requirement of the room, and then the air starts to pick that water back and throw it into the room. In a variable speed system where the compressor changes speed, it is always running. So we could be reducing the amount of moisture removal in the room, but it will never be re-evaporated. That's one advantage which is not listed here, but you should know that. And then the temperature variation. So when the thermostat goes off and thermostat comes on, then this is the blue line, which is showing a wider variation. So when it is first, we can see that this is slow to bring down the temperature, and then there is a variation that is happening as the cycles are going on and off. Whereas in a inverter system, there will be a much smaller band of temperature variations. Lower power bills because of high part load efficiency, and then the reliability of the system, because you put in so many sensors and controls, you can predict what's going to happen, and therefore to that extent preventive maintenance helps run the system longer. And if you look at it from a life cycle cost, then we can make the statement about being cost effective. But if you look at just the initial cost, then an inverter system will always be more expensive than a fixed speed system. Now we look at what are the new things in a multi-indoor AC system. So we need to have an electronic expansion valve. We need to have an element of diversity with Modbus communication. So that means how many units can we connect with one outdoor unit. Typically, diversity brings into fact that we can increase the capacity of indoor units a little more than the capacity of the outdoor unit, because not all of them will operate at their full load all the time. Then we can also look at quick pull down. So we could introduce features like running the compressor at max speed if we are just starting the unit, so that we get the temperature down faster. And we can look at master controller, where we could define that if all the units are switched on, which unit should get priority. So is there a room that you want to be cooling before the other rooms are cooled? And then in the outdoor unit, we can look at envelope control for reliability, which means the compressor is always operating within the pressure and temperature limits that are defined during its design. And there is a need to manage oil return. So refrigerant usually will carry a certain amount of compressor lubricating oil with it. And this oil, it is fine for oil to be mixed with refrigerant and be carried through, but it must come back to the compressor, so that there is always adequate lubrication in the components that are having friction. This is typically a chain where there is a master controller with a unit interface, and this is the inverter which drives the compressor. So the user interface is connected to the master controller. And then we have all of these small individual indoor temperature controllers in a multiple indoor unit connected to a single outdoor unit. So the master controller needs to know what is the cooling demand from each of these indoor units, which will be measured by the set point to actual temperature variation. And then based on the combined demand from all these 6 units in this example, it needs to take a decision on what speed or what percentage capacity the compressor needs to be driven. And that information has to be relayed to the inverter, which in turn will drive the compressor motor RPM in a certain way. So, and then here we also need to get all the temperature information of the refrigerant. So not just the room temperature, but then we also need the compressor data performance related to temperature and pressure. So all of that it needs to do. Then there is some oil management logic. What happens is, at a certain periodic interval, the compressor must be made to run at full capacity, so that all the accumulated oil, which could be stuck in different parts of the pipeline, is brought back to the compressor. And then any diagnostic information has to be logged, any alarm monitoring has to be done, so all that is included. Then for paucity of time, I would say this is a simpler self-explanatory slide, which does most of the part that an inverter is expected to do, which is compressor speed control, derating, cutoff function, and application map protection, and also offers fan speed control. There is another thing called crankcase heater function. So when the compressor is off for a long duration during winter months, we need to be able to keep the compressor warmer than the rest of the system, so that all the refrigerant doesn't migrate into the compressor. If that happens and then the compressor is started after this winter month is over, or winter months are over, then there is a possibility that the entire refrigerant will be taken out, and that can cause compressor failure. So this function is also integrated into. We'll skip this slide. This slide is essentially the application map of protection slide. So any compressor can operate under certain conditions. So this is the safest area, and the 900 to 4200 is the RPM. So 2400, when it is related to, it will be the lowest. 900 to 4200 is the range. 900 will be the lowest RPM. So within this band, any RPM is fine. And then as we look at the different saturation condensing temperature and saturation evaporating temperature, then there are some limits that we begin to see, and that limit is dependent on the compressor discharge temperature, suction superheat, and all those things. So I would not spend too much time because this slide itself can take 15 to 20 minutes. But the whole purpose of putting it up here is that this chart will determine whether or not it is safe to operate the compressor at a certain RPM. So this has to be built into the logic of the embedded control. Now we have come to some concluding slides. The demand for air conditioning we have discussed. Because of all these conditions, it will vary, and the opportunities are to optimize the efficiency for a load and ambient representative of max operating hours in a year. So when we are doing the design, we will get the whole system optimized for highest efficiency for a condition which is representative of the max operating hours in a year. And we may be fine addressing the peak demand at lower efficiency. And then we can factor peak load of grid using smart grid technology. So if that is the case, then we can cool certain occupied spaces earlier to a slightly lower temperature and tide over that peak load factor. And now here we look at what are the things in addition to efficiency, what are the things we need to look at. So ozone, global warming, toxicity. The refrigerant can harm human health. People who are involved in manufacturing, service, installation, maintenance, and in fact finally also the use. So the refrigerant toxicity cannot be accepted. Flammability in some forms is acceptable. There's a standard for it. You can look up the net and you'll find different standards. Increasingly, there is acceptance of some degree of flammability to meet the global warming, the low global warming potential needs of refrigerants. Then we also need to look at initial and operational cost and cost of disposal at end of life. We can't just throw away an air conditioner with refrigerant. We need to dispose the refrigerant properly. Some parts may have things that are environmentally unfriendly and they need to be taken to a facility. So there are rules, regulations. Now, what are the optimizing parameters for a new design? First is that it should improve the quality of life of as many people as possible, which means affordable products and solutions. Then the total life cycle cost is the important parameter, particularly for air conditioning systems, refrigeration, air conditioning, but air conditioning in particular because of the high energy demand with respect to other appliances. And then safety and environmental aspects. Now let's say if we were to make some governing rules, or let's say we use laws, like we have the Bureau of Energy Efficiency defined regulations. So how do we do that? So if you look at a traditional curve, then technology, so more energy efficient technology, the blue line represents, will lead to a higher cost. Initial cost. So more efficient the system, the more will be the cost. However, if you look at the life cycle cost of a system, then the life cycle of the cost of the system will tend to come down, reach a point, and then begin to climb up as we go towards higher efficiency. So if you look at the operating cost plus initial cost, then this is a curve, and we could defining a minimum energy efficiency standard which is at the lowest point of this curve, so that when units are being sold in large numbers, they are at the lowest life cycle cost. And this, if it is made into a law, like Bureau of Energy Efficiency in India has made into a law that units below a certain efficiency cannot be sold in the Indian market, then it has taken up the overall efficiency and therefore reduced the energy footprint of products being sold in the Indian market. And that has led to a lot of elimination of consumption of electricity, and therefore avoidable investment in additional power plants also, or diverting those power plants which have been saved. I mean, the energy can be used for other purposes. So a major contribution happens because of legislation. Otherwise, the tendency of the market is to keep the purchase cost low so that more people can buy the AC, and then they keep burning money on energy cost right up to this point. So here, the compressor the air conditioner operating cost is cheating the user by taking money from him like an EMI. Every month there is an EMI going in the form of a high electricity bill until he reaches this point. Now, this point onwards, the higher purchase cost has to be well considered by a person before he goes in for a better system. So you keep this here, and then anyone who wants a higher system has the freedom to buy more energy efficient systems. So this is called the lowest life cycle cost, LCC. These are examples of how different countries are implementing these legislative levers and keeping the environment, I would say, better protected than it would be if these standards were not there. And this is something that is globally agreed. There's no disagreement on the need for standards and labeling to drive industry towards better performance and ensure a level playing field. With this, I would like to conclude my lecture. Thank you. And if there are any questions, then I would like to open the floor for questions.
Thank you, sir.
Thank you, sir.
Participants are requested to unmute their microphone and can ask the questions. Hello.
Hello.
Sir, may I ask you one question?
Yeah, sure, please. Go ahead.
Whether air conditioning systems gives the maximum performance during full load condition or during the part load condition?
See, if we look at variable speed systems sold in the market as inverter systems, then those systems will give a higher efficiency at part load conditions. Does that answer your question?
Yeah, thank you, sir.
You're welcome.
Hello.
Yes.
Am I audible? Hello.
Yeah. Yeah, clear.
Good morning, sir. This is Dr. KB Sutar from Bharati Vidyapeeth. I want to ask one question. Actually, I have not studied in detail regarding the refrigeration and air conditioning, but as out of curiosity, I want to ask, in the present condition, means whatever the research is being done in India, you explained about the different important components which are actually affecting the performance of the air conditioning systems. So what do you think, in which area presently we shall concentrate on improving the performance of these systems without much investing the amount? Because we know for any research, lot of investment is required. But in the present situation, whatever the resources are available in different research institutions such as IITs and IISCs, so in that case, as per your opinion, what is the component or what is the area in this refrigeration and air conditioning where we can contribute immediately or in near future?
All right. So I can think of two important areas. One is with newer low global warming potential refrigerants, a need for heat exchangers which are optimized. So optimizing heat exchangers, and that optimization can include the tube diameter, the inside grooves of the refrigerant tubes, as well as the fins, the structure of the fins. So that brings us closer to the theoretical cycle from the existing levels. So that becomes one important part of the research effort. The second part would be integrating. So thinking of hybrid systems. See what happens, most of the time we are unable to decide whether to use the evaporative cooling desert cooler or to use the vapor compression system. Vapor compression system is fit and forget. Once you've installed it, then no matter what the environment, it will work. But it is an energy guzzler. And also, if we see a cluster of air conditioners, then they have a outside air temperature warming impact. So if you walk past a corridor where all air conditioners are running, like we have an IIT corridor and then everyone is occupying the room, then we can feel a perceptible change in temperature there. Whereas for a evaporative cooling system, that won't be the case. And then can we use it some form of cooling storage? So if we look at a hybrid technology, that in my mind is an opportunity for us to work on and keep in mind the annual energy cost without compromising comfort. So research oriented on those lines, looking at weather data, looking at heat exchanger optimizing, and combining these two can be a real
yes, sir. Thank you. One more question related to this. If possible, can you take me a few examples regarding the notable Indian efforts in this area? Means they have been recognized.
Okay, so as far as evaporative cooling is concerned, one of the companies I worked for, Acme took technology from a company called Colorado in the US, and they made use of a direct indirect evaporative cooling pad, by which it was possible to get air cooled to within 2 degrees of the wet bulb without adding any moisture. So this is a technology developed by a Russian scientist, matured in the US into a product, and then it doesn't address the comfort needs in India because of climatic conditions, but it was being targeted for a specific purpose designed for telecom cooling, which I was involved in. So that's how I happen to know that. Then other than that, energy efficiency improvement has been taken up now by almost every company. But in the beginning, when I was with the Carrier, we designed the highest energy efficiency window air conditioner in the market that time and launched it. So a commercial product became available. That was one thing. Then in terms of equipment cooling, for MTNL and for DOT, there were air conditioners that were targeting high ambient performance as well as high efficiency. And they were making use of the MTNL units particularly required humidity and temperature control. So this I'm talking about good 20 years back. This was being done. More recently, while in India there's not so much effort, but then overseas there has been technology developed around compression, where for chillers you use a magnetic bearing and eliminate the need for lubrication. So you just raise the shaft and use a centrifugal compression process and maintain the requisite spaces between the rotating shaft and the outer space by a very complex and very fast algorithm, which is taking feedback of the positions of the shaft and altering the magnetic fields to keep the shaft spinning at very high speeds. And that leads to technology where there is no oil that is being circulated in the system. So it's a highly reliable system and allows high part load efficiencies. So when those compressors are used in combination, then very high part load efficiencies up to 10% are possible.
Hello, sir.
Thank you, sir. Thank you.
Sir.
Welcome.
I am Professor Godara from Sabaswati College, Mumbai. Sir, I want to ask a question regarding which refrigerant is best suited for environmental.
Your voice can be a little better. I can hear you, but I am not able to clearly make out your question.
Which refrigerant is best suited for environmental issue? Hello.
Say it again. I heard the environmental issue. Say it again.
Which refrigerant is best for environmental issue?
Well, hydrocarbons for refrigerators, hydrocarbons have been used, so that seems to be well accepted now. Even in the US, for small charge quantities, hydrocarbons have been accepted for small charge applications. And for air conditioning, there has been still work happening. So we don't have the safest refrigerant yet. 410A has taken care of issues related to ozone depletion. So R22 had an ozone depletion potential which was low, which was 0.05, and now this is not there with R410A, but the global warming part continues to worry environmental regulators, and then therefore the shift to R32. R32 brings in a flammability aspect, so it is not classified as a non-flammable like 410A. So 410A is a two-component mixture, whereas R32 is a pure substance and it has mild flammability, which is classified as A2L, and it has a lower global warming potential, but still not low enough to be classified as safe. So there is work happening. We don't really have the molecule yet, which we can say is taking care of everything. For chillers, some newer refrigerants like HFOs are under consideration. With all synthetic refrigerants, there always is a question that what we know is maybe enough, maybe not enough, because a few years down the line we discover another hazard. Like when the freons were discovered, they were non-toxic, and then a few decades later we find that they harm the environment. We took care of refrigerants which harm the environment, and we discovered the refrigerant which don't harm the ozone actually cause global warming. So now again we are going to a change cycle. So the natural refrigerants seem to be more reliable that way. So whether it is hydrocarbons, ammonia, or CO2. But the challenges are that getting efficient systems and getting non-toxic refrigerant becomes a challenge. So this whole area is, it doesn't have a straight one-shot answer that use this refrigerant and it will be fine.
Okay.
If you're looking at places where population is not very high and maintenance practices are good, then for refrigeration applications, ammonia can be a preferred solution. CO2 systems are being considered in Europe for refrigeration applications, and large commercial low-cost applications in residential continue to be R410A, R32.
Thank you, sir.
Okay.
Thanks a lot.
Okay.
So we have a question on YouTube by a student. The question is, why a single psychometric process cannot be used for winter AC systems, whereas for summer AC, one cooling and dehumidification process is enough?
Well, actually, that's not true. If you use hot water to humidify and heat air, then it would be a single step process. So it's a question of how you're designing it.
Participants, do you have any more questions? If you have any questions, do please ask them.
Participants, do you have any question? Hello? Hello? Participants, do you have any question?
So we have one more question on the YouTube. The question says, can nanofluids be used as refrigerants?
I have no experience to be able to make a comment on that. I have not. That's not my area of work, so I will leave it.
Okay, sir. There's one more question as well. What about solid state refrigeration technology?
Well, there is magnetic refrigeration, which is being investigated, shows some promise. But solid state, if by solid state he means using Peltier effect or using some other electronics, then those solutions haven't reached efficiencies comparable to vapor compression systems. So what's happening is that those happen to be some very niche applications. Let's say where the weight to cooling capacity ratio is very critical, and then when efficiency is not so important, then those solutions are used. So I'm aware of some spacecraft applications where abundance of power leads to using some such techniques. It's not mainstream yet.
Hello, sir.
Yeah. Hello.
May I ask?
Go ahead.
Sir, inverter AC systems, and if you compare the conventional air conditioning systems, sometimes we observe that inverter ACs are rated as a 4-star, sometimes a 3-star also, and they are very costly compared with the non-inverter ACs. Then can you enlighten us with the star rating or the energy rating, which is given as a sometimes 3-star, 4 stars, though they are inverter ACs?
So now, fortunately, the Bureau of Indian Standards has put everything in the same process. So when you look at a rating, then the rating says how many kilowatt hours per year are you likely to see as a power bill. So that number becomes the best way to decide which AC to buy, and usually you would make a see. Very often I have friends who ask me what to do. So the way I guide them is that look at the number of operating hours. If you have a room which is used infrequently, like it's a guest room, and you have occupancy which is limited to no more than 25 days in a year, then you can look at a balance between how much you can pay for the air conditioner and what star rating you should buy. However, when you look at your bedroom AC, then I encourage them to look at the most efficient product, because the running cost is going to be very significant. I mean, if someone has a home where there's a homemaker, and she's always at home, and that one unit will run almost 24/7. So then people can make a decision based on an informed decision based on how much more they are paying for a efficient system, and it is all now on the label itself. So if you look at the label carefully, you will find the kilowatt hours per year, which can be a way to make the decision.
Thank you, sir.
You're welcome.
Participants, please unmute your microphone and ask the question.
So there's one more question on YouTube. Are there any research efforts going on for totally different type of refrigerants other than hydrocarbon and the current range of R series refrigerants?
HFOs are being investigated, and companies like DuPont and Honeywell are companies that are working on these alternative refrigerants.
Any question? Participants, any question?
Someone had raised the hand. If you can unmute your mics and please ask the question.
Participant, any question? Thank you, sir. Now we'll conclude the session. I hope all the participants have enjoyed this session. On the behalf of Bharati Vidyapit deemed to be University College of Engineering, I am very much thankful to Dr. Bhupinder Godara sir for such an informative and interactive session on sustainable cooling. Once again, thank you, sir, for joining with us. Thank you.
Yeah, thank you for the opportunity. I wish all the participants the best for the remainder of the program, and wonderful interacting with you. Bye.
All
Thank you,
participants, please note that the next session will begin at 2 p.m. in the afternoon. The link for the quiz is yesterday's quiz is still open. Please attempt the quiz as soon as possible. The link for the afternoon meeting will be the same as the morning one. Thank you.